Look down at your hand, the calcium in the bones, the iron in the blood moving under the skin, the oxygen you just pulled into your lungs, none of it started here. Every single atom in your body, heavier than hydrogen, was cooked inside a star, and then that star had to die to let it out. You are, quite literally, made of dead stars. And stars are dying all the time. Right now, as you sit here watching this, a star somewhere in the observable universe is exploding about once every single second. But here's the thing nobody tells you. Stars don't all die the same way. Some go out like a candle in a quiet room. Some detonate with the force of a billion suns and outshine an entire galaxy for weeks. And which of those fates a star gets comes down to almost one single thing: its mass. How much star there was to begin with. So let's walk up that ladder, from the gentlest death in the universe, all the way to the most violent event since the Big Bang, and I'll show you exactly how every kind of star meets its end. Starting with the ones that refuse to, start at the very bottom. The smallest, dimmest, most common stars in the universe, red dwarfs. Something like 3 out of every 4 stars in the Milky Way is one of these. They're small, a tenth, maybe half the mass of our sun, and they are cheap. They sip their fuel. They burn hydrogen so slowly, so stingily, that a red dwarf can just keep going for trillions of years. Not billions, trillions. Take the smallest ones, and you're looking at a lifespan of up to 100 trillion years or more. Now stop and actually sit with that number, because it does something strange. The universe is 13.8 billion years old. That's the whole story so far, which means not a single red dwarf has ever died. Not one. In the entire history of everything, the universe has not been around long enough for even the oldest red dwarf to run low on fuel. Every red dwarf that has ever formed is still burning right now. The closest star to our own sun, Proxima Centauri, just over 4 light years away, is one of these little red embers, and it will still be quietly burning long, long after our sun is dead and gone. And when they finally do go, they won't explode. They'll just fade, cooling, dimming, shrinking into a dead cinder over stretches of time so long they make the current age of the universe look like a rounding error. That's the gentlest death there is, and nobody has ever been alive to see it. So let's speed things up. Let's talk about a star that actually dies on a schedule we can measure: ours. Our sun is a yellow dwarf, middle of the road, and it has, give or take, about 5 billion years left. When a star like the sun starts running out of hydrogen in its core, it does something that sounds completely backwards. It doesn't shrink, it swells. The core contracts and heats up, the outer layers balloon outward, and the sun becomes a red giant hundreds of times its current size. First it swallows Mercury, then Venus, and Earth. Earth is either swallowed whole or left behind as a scorched, airless rock orbiting a monster. Either way, it doesn't matter much, because long before that, about 1 billion years from now, the sun gets bright enough to boil our oceans dry. So the planet's story is over well before the sun's is. But the sun itself isn't done. After the red giant phase, it starts gently shrugging off its outer layers, puffing them into space in glowing shells of gas. We call that a planetary nebula, which is a terrible name because it has absolutely nothing to do with planets, but astronomers named it 300 years ago and now we're stuck with it. These are the most beautiful objects in the sky. The ring nebula, the helix, those glowing eyes you've seen in space photos, those are dying stars caught mid-collapse, lit up from the inside, and it only lasts about 10,000 years. A cosmic blink. When the gas finally clears, what's left sitting in the middle is the naked, exposed core, and that little core changes everything. That core is a white dwarf, and a white dwarf is one of the most extreme things you will ever hear described. Take everything left over from the sun, hundreds of thousands of times the mass of the Earth, and crush it down into a ball about the size of the Earth. That's the density. 1 teaspoon of white dwarf material would weigh several tons back here on the ground. It isn't fusing anything anymore, there's no fire left in it. It's just a glowing ember, unbelievably hot, radiating the last of its heat away into the dark. And here's the quiet, eerie part. A white dwarf cools over billions, eventually trillions of years, fading from white to yellow to red, until it finally goes completely dark and cold. A black dwarf. A star's corpse. Invisible. Drifting. Except, and I genuinely love this, there are no black dwarfs anywhere in the universe. Not one. Not yet. It takes so unimaginably long for a white dwarf to fully cool that none of them anywhere has had the time to finish. The universe is, once again, too young. So the calm death of a sun-like star ends in an object that we're certain exists, and that has literally never happened. Unless that white dwarf has a friend. Because if it does, everything I just told you goes straight out the window. Say our white dwarf isn't alone. Say it's orbiting another star close. The white dwarf's gravity is so intense that it starts stealing gas straight off its neighbor, pulling it in, piling it on, getting heavier and heavier and heavier. And there is a hard limit here. A line no white dwarf is allowed to cross. It's called the Chandrasekhar limit, about 1.4 times the mass of the Sun, and it was worked out by a 19-year-old physicist named Subrahmanyan Chandrasekhar, doing the math on a boat to England in 1930. Push a white dwarf past that line, and it simply can't hold itself up anymore. In about 1 second, the carbon inside ignites all at once, and the entire star detonates in a runaway thermonuclear explosion. This is a Type 1 supernova, and the white dwarf isn't damaged, it's gone, blown into loose atoms. Nothing left behind. Now here's why that matters to you. Because every one of these explosions trips at that same exact tipping point mass, they all blaze with almost exactly the same brightness, which turns them into cosmic measuring sticks. In 1998, two rival teams of astronomers used these exploding dead stars to measure how fast the universe is expanding, and got a result that stunned them. The expansion isn't slowing down, it's speeding up. That discovery is what we now call dark energy, and it won the Nobel Prize. So a dead star, quietly stealing gas from its neighbor and blowing itself to pieces, is how we found out the fate of the entire universe. Not bad for a corpse, but so far we've been playing in the shallow end. Small stars, medium stars, time to go big. Now take a star with 8, 10, 20 times the mass of the Sun. These monsters live fast and die young, a few million years instead of billions, and they die in a way that is genuinely one of the most violent processes in all of nature. And one of them is hanging in your sky right now. Look up at the constellation Orion this winter. That bright reddish-orange star on his shoulder is called Betelgeuse. It's a red supergiant, maybe 15 to 20 times the mass of the Sun, and it is going to do exactly what I'm about to describe. Maybe tonight, maybe 100,000 years from now, nobody knows which, but when it finally goes, it will be bright enough to see in broad daylight. A big star is a furnace with layers. In the core, it fuses hydrogen into helium. When the hydrogen runs low, it cranks up the heat and starts fusing helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon, and each stage burns faster than the one before it. The hydrogen might last millions of years, but right near the end, the star is fusing silicon into iron in about a single day. And then it hits a wall, because iron is the dead end. Every fusion reaction up to iron gives the star energy, but fusing iron takes energy instead of releasing it. So the instant the core turns to iron, the fire that has held this star up for millions of years against its own crushing gravity just stops. And gravity has been waiting the whole time. In less than 1 second, an iron core the size of a planet collapses in on itself. The outer layers fall inward at nearly a quarter of the speed of light, slam into the ultra-dense core and rebound, and a shockwave supercharged by a blast of neutrinos rips the entire outer star apart from the inside out. That is a core collapse supernova. And for a few weeks, one single dying star can outshine every other star in its galaxy, 100 billion suns combined. You can see one from clear across the universe. We've actually watched it happen. In the year 1054, Chinese astronomers wrote down a brand new star that appeared in the sky so bright it was visible in broad daylight for 3 straight weeks. That was a star dying. And today, if you point a telescope at that exact spot, you can still see the shredded, glowing guts of it flying apart. We call it the Crab Nebula, nearly 1,000 years later. And what one of these explosions leaves behind in the wreckage might be the strangest object of all. When that iron core collapses, gravity crushes it so hard it forces the electrons and protons to merge into pure neutrons, jammed shoulder to shoulder. What's left is a neutron star. And I need you to really picture this one. Take about 1.5 times the mass of our entire Sun. Crush it into a ball about 20 kilometers across, the size of a city. That's it. A single teaspoon of neutron star material would weigh about 1 billion tons, as much as a mountain. Right here in your hand. It is the densest thing in the universe that isn't an actual black hole. And they spin. When something big collapses into something tiny, it spins up. The exact same way an ice skater whirls faster the instant she pulls her arms in. Some neutron stars spin several hundred times every second. The fastest one we've ever found rotates 716 times per second. A city-sized ball, heavier than the Sun, spinning so fast it would blur. And as they spin, they fire beams of radiation out of their magnetic poles. If one of those beams happens to sweep across Earth, we catch a pulse. Tick, tick, tick. So perfectly regular that when we found the first one, we genuinely wondered if it was aliens signaling us. We call them pulsars, and a rare few of them are far worse. A small number of neutron stars wrap themselves in the single most powerful magnetic field found anywhere in the universe. We call those magnetars. Get within 1,000 kilometers of one, and its magnetic field alone would tear the atoms in your body apart. In 2004, one magnetar clear on the far side of our galaxy let out a single flare that for a fraction of a second disturbed the Earth's upper atmosphere from 50,000 light-years away. So a giant star dies and leaves behind a spinning city-sized nucleus heavier than the Sun. But what happens? if two of those find each other. Picture two neutron stars, both of them corpses of dead giants, locked in orbit, spiraling closer and closer over millions of years. Eventually, they slam together. And when they do, they shake the fabric of space-time itself. On August the 17th, 2017, we felt exactly that. Gravitational waves, actual ripples in space, rolled through the Earth, sent out by two neutron stars that had collided 130 million light-years away. We didn't just see it, we felt the shape of space wobble. The collision is called a kilonova. And here's what it makes. As those two neutron stars tear each other apart, they fling out a spray of neutron-rich matter that instantly forges the heaviest elements on the periodic table: gold, platinum, uranium. That one 2017 collision created an estimated 10 Earths worth of gold and platinum, and about 16,000 Earths worth of heavy elements in total, in a matter of seconds. So the gold in a wedding ring, the platinum in your phone, it wasn't made on Earth, it was forged when two dead stars destroyed each other somewhere out in the dark before the sun was even born. Go ahead and let that reframe your jewelry. Now, we've covered small stars, medium stars, and the giants that leave neutron stars behind. But there is a class of star so massive it doesn't get a neutron star. It gets something darker. Push past around 25 times the mass of the sun, and when the core collapses, not even the neutrons can hold the line. There is nothing left in physics strong enough to stop it. The core keeps falling, past the neutron star stage, past every known limit, down into a single point of impossible density, a black hole. A place where gravity wins so completely that not even light can climb back out. Sometimes this still comes with a spectacular supernova on the way down. But sometimes, and this is the part that genuinely unsettles me, it comes with nothing at all. In 2009, astronomers were watching a star 25 times the mass of the Sun in a galaxy 22 million light-years away. It briefly flared up, more than 1 million times brighter than our Sun, and then, when they looked back in 2015, it was just gone. No supernova, no explosion, no debris field. A star that enormous simply winked out of existence, like somebody flipped a switch. The best explanation is that its core collapsed so directly into a black hole that the entire star got swallowed before it ever had the chance to explode. It's called a failed supernova, and the estimates say up to a third of the most massive stars might die exactly like this. Not with a bang, but with a shrug. Here one decade, gone the next. But if you want the loudest death in the universe, the actual record holder, we have to go bigger still. At the very top of the ladder sit the true giants. Stars 100, 200 times the mass of the sun. Stars so massive that the core doesn't just make heat, it starts making matter. The gamma rays trapped inside are so ferociously energetic that they begin spontaneously turning into pairs of particles, electrons and their antimatter twins, positrons, popping into existence straight out of pure light. And the moment that happens, the pressure holding the star up suddenly drops, the core caves in, and the whole thing ignites in one single catastrophic runaway. This is a pair-instability supernova. And it doesn't leave a neutron star, it doesn't leave a black hole, it leaves nothing. The entire star, all 200 solar masses of it, is blown completely apart, one of the brightest explosions the universe is capable of, and there is not one atom of the original star left in one place. And then there's the true worst-case scenario. Some of these dying giants, as they collapse into a black hole, fire twin jets of energy out of their poles at very nearly the speed of light. If a star does that while it happens to be pointed at you, you get a gamma ray burst, the single most powerful explosion since the Big Bang itself. In just a few seconds, one of these can release more energy than the sun will put out over its entire 10 billion year lifetime. Some scientists suspect that a gamma ray burst may have stripped away part of Earth's ozone layer and helped trigger a mass extinction. 445 million years ago, though I'll be honest, that one is still a hypothesis, not a settled fact. But point one of these at a nearby living planet, and you don't get an extinction. You get sterilization. So that's the ladder. The smallest stars fade so slowly that none has ever finished dying. Stars like the Sun swell, shed, and cool into corpses that haven't had time to go cold. Their heavier cousins detonate and leave behind spinning cities of neutrons. And the true giants collapse into black holes, or blow themselves so completely apart that nothing remains at all. Every single one of those fates decided by one number how much star there was to begin with. And here is where it all lands. Right now we are living in the bright age of the universe, the era when stars are still being born. But star formation is already slowing down. Run the clock far enough forward, and the very last new stars will be red dwarfs, those stingy little survivors, burning quietly for trillions of years after everything else has gone dark. And one day the last one of them will flicker out, and the universe will go black for good. No stars, no light, just cooling embers drifting in the dark forever. But not yet. Right now, the sky is full of them, living and dying, and every atom of you was forged inside one that already died, so that you could be standing here to look up at the rest. Every star in the universe dies. That's the deal. The only difference is how loud. So the next time you look up, remember, you're not looking at the sky, you're looking at a graveyard and a nursery at the exact same time. And you are made of the ones that already went. If this rewired how you see the night sky, there's one more question waiting for you. What actually happens if you fall into one of those black holes we just made? That video is right here. I'll see you inside.